our second unit. We're going to be talking about tensor decompositions for a couple of lectures. So today I'm just going to give you a friendly introduction to tensors. Really, if you sort of are thinking about matrices, a lot of times your intuition is wrong when you start thinking about tensors. So actually, what I'm going to do is I'm going to start off with some of the introduction to historically why people got interested in tensors in the first place, revisiting one of the classic problems in statistics, and going back to Charles Spielman's work in 1904. But really the outline for today is we're going to be talking about the hope for tensor decompositions, the disappointment, and then we're going to end on an optimistic note about how we can actually start to use these things in learning. So, the first thing to ask is, what is a tensor? So how many people have seen tensors before? All right, so let me, I'm still not going to assume it, but let me start with the basics. So, you can think about it just as a collection of numbers, but we'll care about things like the rank and the border rank and so on. So, it's a generalization of matrices to potentially more than two indices. And just to get our definition straight, so we'll oftentimes talk about the order, of a tensor is the number of indices that we need to address this, collection of numbers. So just to make sure we're on the same page, an m by n matrix is an order 2 tensor. But more generally, we're going to focus most of our attention on order 3 tensors because there's certain degeneracy things that happen with matrices that in general, given just the matrix, you can't pull out a unique way of describing its factors. But once we start to have tensors, they're algebraically more rigid objects, which is what will give us power in sort of learning in statistics that when we think about the tensors as coming from observables from some learning problem, we'll actually have a unique way to go back to the parameters that actually generated the model. So that's the pattern about how we're going to do it. But first, I want to develop some familiarity with thinking about what tensors are and what sorts of properties, go wrong with them. So today we'll mostly be interested in order 3. Which we can think about as m by n by p size objects. And you can just think about them as collections of matrices, for example. So we could think about them as p m by n matrices that are just stacked. So these are 3-dimensional objects now. So actually there's a sort of cool story. Let me now actually define the rank of a tensor, and then we'll get into sort of Spearman's work. But one of the crucial definitions about these is the same way we have rank for matrices, we can define the notion of rank for tensors. So let me define it implicitly by what a rank 1 tensor is. So rank 1 third order tensor is something to the form. Well, we're going to denote it by U tensor V tensor W, but in particular, the entry in ijk for this tensor is just the product of the ith entry of U times the jth entry of V times the kth entry of W. So pictorially, all that's going on is that you have this third order tensor, which you think about as drawing in 3 dimensions. And you have 3 vectors, U, V, and W, that compose this rank 1 tensor. And then if you care about the entry in ijk, all you're going to do is you're going to explicitly take the product of ui times vj times wk. So of course, this is exactly the classic notion of what a rank 1 matrix is. It's just the outer product of 2 vectors. So the same way a rank 1 third order tensor is just the outer product of 3 vectors. And for fourth order tensors, you get the same thing, an outer product of 4 vectors and so on. So this is what our set of rank 1 tensors are, and it gives us a way to define rank more generally. Because for a general tensor, we can think about its rank as what's the minimum number of rank 1 objects we need to add up to get it. So that'll be the rank. All right, so these are some of the crucial definitions that we're going to start with today for thinking about tensors. But I want to warn you, there are all sorts of pathologies that can happen. So we'll get into that in a minute. But the first thing I want to do is I want to tell you a story that tells you part of the reason for considering tensors to begin with. So how many of you guys have heard of factor analysis? Anyone? So just one. Well, actually, factor analysis is one of these really popular, important things to do in statistics, but it goes back to the work of Charles Spearman, who was a famous psychologist around the 1900s. So Spearman actually had a famous hypothesis. He was trying to understand, the different types of intelligence students have. So what his belief was that there are fundamentally 2 types of intelligence. Mathematical and verbal. So I'm not sure I agree with that. So he's somehow implicitly claiming that these 2 are uncorrelated, which as someone at MIT I take offense to, but let's go with it. So this was back in the 1900s when it was okay to say those things. But what his approach was we can think about it in our language as looking for a nice matrix decomposition. So, he believed there were 2 types of intelligence, so this is called Spearman's hypothesis. And what he did was he took, a huge collection of how students did on different tests. So he had this matrix of 10 different types of academic tests students have taken, and he had 1,000 students, and he put in here mathematical scores for these students. And what he believed, the way that he tried to test out this theory that there are 2 types of intelligence was he believed that how a student did on some particular exam was just a function of 2 things. The student's aptitude for mathematical versus verbal reasoning, and what that test tests. So to what extent is that test about mathematical or about verbal or about some combination between them? So, a lot of times this is called, one of the starting points of latent variables, is that he believed that each student was described by these hidden variables, and same with each test. And then once you understood these hidden variables, that you could explain all of your data in a nice, crisp way. So, what he set about doing was he took the best, rank 2 approximation. So this is something that we already talked about, is the notion of looking for the best rank k approximation. So can someone remind me mathematically how we might go about doing that if we have this huge matrix?
Truncate the SVD down to the top two singular values.
Yes, exactly. The natural way to do this is to do the truncated SVD. This was something we talked about in the first lecture, where we can write this matrix as in terms of its singular value decomposition, and it gives us a natural way to, when we care about the best rank 2 approximation in terms of the spectral norm or in terms of the Frobenius norm, the answer is always the same. It's the truncated SVD, where we take the first 2 factors. But what he got then, you can write it out as just the product of 2 matrices where the inner dimension is 2. So we got some rank 2 approximation to this matrix. And what he hoped was that these were the latent factors, right? That for each, he was hoping that one of these 2 rows represented mathematical aptitudes, and the other one represented verbal aptitudes, and that for each student, the corresponding column would just be what fraction, what the relative aptitudes were in those 2 types of intelligence. And what he hoped here is that the same thing was true, that the columns represented, the different types of intelligence, and that each row here represents a test, and it would tell you how much that test tests mathematical versus verbal intelligence. So that was the basic idea, but there's a rather fundamental flaw to this approach, which is even a mathematical approach. So even if you believed Spearman's hypothesis, which I don't, but even if you believed it, that there were only 2 types of intelligence, the issue is you're given access to a matrix M, and you're hoping that there's a nice factorization in terms of some rank 2 factorization that almost agrees with the matrix. But the issue is that this factorization is in no sense unique. There's no reason that the SVD would have given you a nice intuitive explanation of your data, even if there was one. So what I'm trying to say mathematically is that we can think about this, this way. What if I call this matrix U, I call this matrix V transpose, and we have the property that our observed data equals, approximately equals U times V transpose. So I could just as well create another explanation where I put in some 2x2 orthogonal transformation. All I do is I put it in, and I put its own inverse right next to it, so they definitely cancel. But what this gives me a way of doing is creating a different factorization that also explains your data. So what I'm getting at is you have a scientific theory here that there is some nice factorization that you can look at and interpret and derive some sort of intuitive meaning from. But why should you be able to recover that actual factorization given just M? So this is the sense in which it's good to sort of move beyond matrices, because this type of degeneracy, so this is actually a really important problem in factor analysis. Sometimes it's called the rotation problem. That when you have a nice factorization, you can find another factorization just by rotating what you found. And that'll give you a perfectly good explanation as well. So the issue is, how would you find a nice factorization not modding out by symmetries like rotation? So tensors are actually going to give us a way to answer that, because their decompositions are much more rigid. And you'll see that at the end of the class, we're going to give an algorithm for actually uniquely finding the factors that compose a tensor under fairly general conditions that give us a way around this rotation problem. So, the way that we're going to think about this will sort of lay the groundwork for, the next few lectures when we apply tensor decompositions to various problems. But already you should think about it that, here is sort of a hidden variable model that Spearman was proposing, was that conditioned on, the hidden observations of what a student's aptitude are for these different types of intelligence and what the test is testing, that you should be able to predict the data. So you should think about them as finding two conditionally independent factors, which are independent conditioned on some variables you don't have access to. Now, the same way that you can't uniquely find the parameters of this model just given two conditionally independent random variables, once you're given three, you can. So what we're going to do at the end is we're going to talk about an algorithm for tensor decompositions, but later what we're going to do again and again is we're going to apply it to different models, things like phylogenetic reconstruction, hidden Markov models, even back to topic modeling, where what we'll do is we'll just ask the question, where can we find three conditionally independent random variables, and how can we use the tensor decomposition algorithms to learn parameters of the model? Does that make sense as an outline? Any questions? All right, so I promised you in the outline that we're going to start with the disappointment. So let's talk about tensor decompositions and be really pessimistic about all the things that go wrong, just so that you don't, make these mistakes, because a lot of stuff goes wrong in tensors. And let's think about this as, trying to build the parallel between, what's true for matrices and what we hope, or at least could hope, would be true for tensors. So, okay, so for matrices, it's easy to compute the rank. Now, unfortunately for tensors, it turns out to be NP hard to compute the rank. This is a paper of Hostad from 1990. It gets a lot worse from there. So let's see. So for matrices, we have nice things like the dimension of the span of the columns is equal to the dimension of the span of the rows is all equal to the rank of the matrix. So all I'm saying is you take your matrix, and on the one hand, you take all of the columns, look at that collection of vectors. Whatever the dimension is of that span is the same thing as if I take that matrix and I look at the different rows and look at the span of the rows and ask what its dimension is. This is, of course, a really powerful statement that row rank equals column rank. There are lots of clever ways even a basic linear algebra fact like this gets exploited in things like approximation algorithms. But no such luck for tensors, right? So, how could you try and get this to work out? Instead of having an array of values and where you can look at the different columns or the different rows, you have a 3x3 object. And, one of the things that you could try is you could try looking at all of the different, length n vectors. There's n by p of those things. But, can anyone see the problem with trying to compute its rank by looking at the dimension of their span?
It seems like if two columns are in the same row, then it's different than if they're diagonal.
Yeah, yeah, definitely. Or another way of even thinking about this issue is that, I have m by p vectors in Rn. That's bad because whatever that set of vectors is, it only has, the dimension of its span can only be at most n. I can definitely construct tensors whose rank is much larger than n. But, going back to, Lotzi's point, something else goes wrong here, which is different ways of cutting up the tensor also suffer from the same basic issues. What if instead of cutting it up into m by p vectors in Rn, where I take all of these different, vertical vectors, what if instead I took slices through it? And in this case, I would get p matrices in Rn by m. So the issue is, for example, each of these, matrix slices, what if it just had ones along the diagonal? If I look at something like what the span of those matrices are, they're all scalar multiples of each other, so I don't create any different matrices, even though the rank of this tensor is clearly, n, just because the simple object through it has large rank anyways. So there are lots of issues that go wrong, that there's no way to sort of take a tensor and cut it up into simpler objects the same way for matrices that you can, as a way to deduce what the rank is. All of the natural approaches really do go wrong. Let's continue with disappointment. So, there's a lot of stuff that we learned about, matrices from the SVD. That was a really powerful way to think about, best rank K approximation and how to derive it. So what I claim is, for matrices, and we've already talked about this exact issue, for matrices, the best rank K plus 1 approximation and best rank K approximation, so K plus 1 versus K, are related. So if I take some matrix and I ask you what does its rank K plus 1, best rank K plus 1 approximation look like versus what does its best rank K approximation look like, these are actually intimately related objects. Anyone see why?
The one SVD difference? Because
Yeah.
we truncated it?
Yep. So they're just different truncations of the same SVD. Or to put it another way, if I gave you a matrix and told you what its best rank K plus 1 approximation is, you could actually get the best rank K approximation from that object. All you would do is you would take that K plus 1 rank approximation and you would compute its best rank K approximation, and that object that you would create would turn out to be the best rank K approximation for the original matrix too. So in fact, the best rank K plus 1 and rank K approximation just differ by one rank 1 factor, which is great. So they share all of their other common factors, which are things that you get from the truncated SVD. Does that make sense? Now for tensors, there's no such luck. The best rank K and the best rank K plus 1 versus best rank K approximation need not share any factors at all. They can have nothing to do with each other. That's bad, right? This is already starting to look pretty grim. Let's make it worse.
Is there any intuition about why that's the case?
let me come back to that. I'm going to show you, it's going to get worse before it gets better. Let me show you some intuition for the other stuff that goes wrong. And then I think this thing doesn't look as surprising in light of those, because I'll give you some concrete examples for other things. But that's a good question. All right, this one's actually really frightening. Yep.
So the rank computation for this is identified in what parameters, like the rank or in the sub-dimensions?
As in, if the rank is small, can you compute it better? It's a good question. I don't know of anything that does better for smaller rank in terms of the computation. So I don't know offhand, for example, if your target rank is constant, whether you can solve it in P. Now, it turns out when we covered NMF, actually it is solvable in P when the inner dimension is constant. But there are a few of these types of problems which, some get a lot better when the target is, small inner dimension, and some don't seem to. So NMF definitely is easy when the inner dimension is constant. There's something based on systems of polynomial equations that maybe we'll cover later. But for things like matrix completion and tensor decomposition, I don't know the answer. And I don't even know whether there are lower bounds that say that you can't do that. But that's a good question. So let's make it worse now. All right, this one's really scary. So for matrices, if you have a real matrix, it's min rank decomposition over R and over C are the same. Right? So as in, you have this matrix with real values in it, to keep you honest that you don't intrinsically need complex values to recover the matrix. And what you're asking is, what is the smallest inner dimension so that I can find the product of two matrices? Now, they're not non-negative like they were in NMF, they're arbitrary. What's the smallest inner dimension so that we can exactly equal this? This is just whatever the rank of the matrix is. What I'm saying is when you start off with a real matrix, entry-wise real matrix, there's no need to actually put in any complex values in here to begin with. You might, without lost generality, just look at the field over R. So the fact that the rank has a definition, which is independent of which base field you're considering, is great. That's an awesome property for the rank of matrices. There's no such luck for tensors. Can the rank of the rows?
Can there be a complex decomposition but not a real decomposition?
Oh, but so there's always going to be a good question. There's always going to be a real decomposition, because one of the things I can do if I want to do something truly stupid is I could just think about the outer product between three of the basis vectors, EI, EJ, and EK. That's going to allow me to pull off just one entry from the matrix. So I can always get away with doing n cubed. In fact, if you're more intelligent about it, you can always do n squared. And the largest the rank of a third order tensor could be is about n squared. Actually, it's a bit funny because people work on, in algebraic geometry, what's the right constant in front of that n squared in terms of, do there exist tensors with that type of rank? And for order k in general, the rank can be roughly n to the k minus 1. There are much easier ways to see that it's roughly in that right ballpark. But I guess what I'm saying is that these are all the things which you never even thought about for matrices, and they just happen to work out. All right, last frightening example, and this one I'm actually going to show you what goes wrong, so that I'm not just alluding to this scary beast out there. Yep.
I'm not sure if I understand the difference, the problem.
Yep.
Like for matrices,
Yep.
what do you mean? Like it's the same for R and C?
So
I'm
what I
not
mean
quite sure if I
here
understand.
is you start off with a matrix, which is entry-wise real. So it's keeping you honest that there's no reason from just looking at the matrix that you might need to go to complex values to explain it.
Okay.
And when you start off with an entry-wise real matrix and you look for a factorization of this form, which has minimum inner dimension, you see if you restrict the entries here to be over R, then that's more constraining than being over C. But constraining yourself is not an issue in this case. When the original thing has entry-wise reals, then in this factorization, the smallest inner dimension you get is actually the same whether you require them to be reals or you even allow them to be complex values. This is not true for tensors, that if you start with a tensor and ask for its minimum rank decomposition as a sum of rank 1 tensors, there's a difference, even if you start off with a real tensor, between asking for what that smallest R is when you allow real or you allow complex values.
Okay. Interesting.
So that's the issue. All right, and all of this stuff, what it's hinting at, you should think about it as hinting at the idea that the rank is not that well defined and is a very brittle object, right? Because on the one hand, we have this hint that it's easy to compute versus hard to compute. It admits many equivalent characterizations, and the natural way to generalize that is not true. And here it has this sort of downsampling property that best rank k can be obtained from best rank k plus 1, which also doesn't happen. And here what I'm saying is it's not field independent based on what you allow the entries in your decomposition to be. But in fact, there's something called border rank, which for matrices is the same thing as rank, but for tensors is not. So border rank, intuitively what it asks is, can you find what's the fewest number, the smallest rank, where you can find an arbitrarily good approximation to a matrix, to a tensor or to a matrix. For a matrix, that turns out to be the same thing. For a tensor, it turns out to not be the same. So, border rank of some tensor T is the smallest R, so that for all epsilon greater than 0, there is some factorization such that T minus sum over I equals 1 to R, ui tensor Vi, tensor Wi is at most epsilon. So what this means is, what we're asking is, what's the smallest R, so that whatever epsilon you give me, arbitrarily small, there exists some rank R tensor, which is explicitly given here, because I'm giving it to you in terms of its rank decomposition, which, how well it approximates T, and say it gets all of the entries right, you want it to be close within an epsilon. So you want that all of the entries in this rank R approximation are epsilon close to the entries in T. And so this is, a natural definition, right? Is you should think about this intuitively as what's the smallest R, so that when I restrict myself to rank R tensors, I can get arbitrarily good approximations to the tensors. Now I claim that for matrices, we already know that border rank, you can define the notion of border rank, that border rank would be equal to the rank for a matrix, right? Because if I give you a matrix and I ask you to approximate it as best you can with a rank R factorization, there's a limit to how well you can do. Because essentially the best you can do is something like the truncated SVD. but that's not true for tensors. So let me give you that example, because it's a sort of illuminating one to think about. So let's say our tensor looks like this. So this tensor is in R 2 by 2 by 2. Just a 2 by 2 by 2 tensor, nothing simpler than that. And this is the first matrix slice. This is the second one. So just stack this on top of this, and that's our three-dimensional object. Now the issue is that this is a tensor, which its border rank is not equal to its rank. So it's not hard to show that actually the rank is 3, that you can't exactly explain this tensor with fewer than 3 rank 1 terms. And you would do that just by picking off the ones individually for each of your terms, your factorization. But the issue is that even though it's not rank 2, you can get arbitrarily close with rank 2 approximations. So any guesses about how you might go about doing that? It's a funny little puzzle, actually. So what I claim is that the only way that border rank would be not equal to the rank of a tensor is if in some way these factors that you're using create cancellations. They add in something really large and then they subtract off something really large, so that they kill it. And that's what allows them to sort of get finer and finer approximations. So there's actually a trick here, which is, what we're going to do is we're going to add in an n here, a huge value, and then we're going to subtract it off. And that's the way that we're going to get arbitrarily good approximations to it. So the way to think about it is, consider the following type of tensor: n, 1, 1, 1 over n, 1, 1 over n, 1 over n, 1 over n squared. So I'm going to call this tensor S. So this is, again, just some tensor, which is 2 by 2 by 2. Can anyone tell me what the rank of this tensor is? Yes, 1. 1, right? Because the way that I could do this now is I could think about it as the outer product times some scaling factor, n. So this is explicitly what its rank 1 factorization is. If I took 1 and 1 over n and took its outer product of itself 3 times, then I would get the entry 1, 1 over n, 1 over n, 1 over n squared, 1 over n, 1 over n squared, 1 over n squared, 1 over n cubed. And all I do is I'm shifting that up by n here to actually get my original thing. So this is a rank 1 tensor. And now I can do some tricks to actually get an arbitrarily good approximation to t, because, another rank 1 tensor is just the following. It certainly has rank 1 again. It just has 1 non-zero entry, so I can easily explain it as the outer product of basis vectors times a scalar. This is again in 2 by 2 by 2. But now the point is that t minus r minus s gives me this tensor, which, as I take n to be arbitrarily large, I get finer and finer approximations. So this is the first example where border rank is not equal to a tensor rank. So it turns out, rank of T over R or over C, doesn't really matter, is 3. And yet the border rank of T is 2. So this is sort of a good example of the pathologies that happen in working with tensors and dealing with their ranks, is that sometimes the best explanation you can do involves adding in something really large. Like think about taking this tensor and adding a huge value n here, and then it becomes approximately rank 1, but then you're going to subtract off that value later. So the problem is that the things in your rank 2 approximation, even though the norm of T, its entries are not growing, they're just 1s and 0s, to get finer and finer approximations, you're actually growing the norms of these things that you are adding in to represent it. So they're actually getting larger and larger as you ask for finer and finer approximations. And the fact that the rank of T is not equal to 2, even though you can approximate it arbitrarily well, is really more of an algebraic fact about systems of polynomial equations, that you can't perfectly do this, that you can only approximate it. So that's one of the major issues, is that tensor rank has these pathologies, that it's really about solving some system of equations. It's not about finding arbitrarily good approximations. Yep.
So this seems to be saying that the set of tensors that are ranked at most 2 is not a closed set.
Yes.
But would that be true for rank 1? Rank 1.
Sorry. So the set of tensors, which are rank what?
So this example shows the set of tensors that's ranked at most 2 is not closed.
Yes. Exactly, because I'm creating a limit of rank 2 tensors whose limit point is exactly this rank 3.
But the set of rank 1 tensors is closed. Is that right?
Yes.
Okay.
Yeah. But the issue is that this also doesn't happen for matrices, right? Because here I'm cheating a little bit, because the notion of how close I'm looking for these guys, for this rank R object to approximate T, is I'm doing something like I'm looking at its, max entry. I'm saying entry-wise you get epsilon close. Now if I do something, this is, the border rank doesn't really change under different notions of what norm you're using to measure these guys. But if you think about matrices for things like a spectral norm, then we know that this really can't happen, right? Because if I give you a matrix and ask for its best rank R approximation in spectral norm, we know it's the truncated SVD, and you can do no better. So this issue of being able to create arbitrarily fine approximations does not happen for matrices. So are there any questions about this? All right, one last one. So this, if you can answer this question, I can just give you your PhD thesis. I have them in my bag. So you'll probably end up teaching at MIT next year the advanced complexity class. But so the issue, what I alluded to was that a random tensor has very large rank, third order tensor. So it'll have rank about n squared. Okay? So now think about the exercise of trying to explicitly construct a tensor that has large rank. One of the things I can do is I could do something stupid, like I could just take my first slice and put the identity matrix there. That's something which that matrix has rank n, and that tensor definitely has rank n too. But the issue of actually trying to beat n significantly would imply some sort of shocking consequences in complexity theory. So that'll be the last sort of fact. This follows from work of Ron Raz, that if you give an explicit n by n by n tensor, you know, something that you could write down, you're not saying generate one randomly. You can give an explicit n by n by n tensor where the rank of t is at least n to the 1 plus epsilon for any epsilon you choose. It would actually give us the first non-trivial circuit lower bounds in a general model. So, you know, most of you, I hope, believe p not equal to np. Most people believe that even, you know, SAT is going to require exponential size circuits. Anyone know what the best circuit lower bounds we have for SAT are that are unconditional? Also due to RAS, 5n. So if you can actually prove any, you know, n to the 1.1 lower bound for the rank of an explicit tensor, you know, you can construct any tensor you want. There's actually a way that Raz gave of using that to construct a, you know, computational problem, which would have a circuit lower bound that you need at least n to the 1 plus epsilon circuits to do it. So the sort of disappointing fact in complexity theory is we have lots of wonderful conditional lower bounds. Things like if p not equal to np, then we have all sorts of hardness approximation results. But actually giving unconditional results, it's very tricky, and it's related to the issue of finding explicit tensors that don't have linear rank, the same way that a random, you know, n by n by n tensor will have rank close to n squared. Giving any explicit example would have, you know, strong statements in complexity theory.
What we're saying here is that for any n that is given an algorithm to build for any n tensor, that not
yeah, so I mean, you have to be a little careful on what you mean by explicit here, but certainly if you give like a parameterized family, you know, for all n, you know, give me something which has that type of rank bound, then it will imply the statement. There's the issue that sometimes when you talk about explicit, you just mean, you know, is there a polytime algorithm to construct the thing? And I'm not sure that that implies it, but I should double check that.
Would a random tensor also have border rank n squared, close to n squared? Or?
I think so, but I don't know offhand. Actually, I do know. Yes. Yes, but good question. Any other questions? This is sort of a long sequence through the disappointment. No, so border rank cannot be greater than the rank because, you know, for a definition of border rank here, you know, if T really did have rank R, then you would just choose whatever its decomposition is into rank 1 terms. That would be a perfect approximation, so it would satisfy this definition. See, the extra power for border rank is that, you know, it's the order of quantifiers, is that you choose the epsilon and I'll choose the decomposition. Whereas what rank is saying is that there's one decomposition that works for all epsilon. And that's the version to sort of compare rank and border rank, is that border rank allows you an extra order of, you know, quantifiers that given the epsilon, you can then choose how to approximate it. That's the same way that here in this example, our factors grew. You know, as you give me an epsilon, I choose n to be larger so that I get a finer and finer approximation. All right, so I think it's good to end on an optimistic note. So despite all of this pessimism, there actually is a simple algorithm for decomposing fairly general tensors. So they're not going to work in all cases because otherwise we could, you know, compute the rank of the tensor and violate, Hastad's hardness result. But it'll work in general enough conditions that it'll be really useful for applications in learning. And the funny thing is, just to tell you a bit of the historical perspective, the result I'm about to give you has been, to my count, rediscovered in every decade since the 70s under different names. So the previous time I taught this course, I used it as an opportunity to dig into some of the history. And I thought, oh, everyone's calling it Chang's lemma. It's not that. So I started calling it something else because I found an earlier reference. And then over the winter, I found an even earlier reference. And now I have to go around correcting people who started calling it something else because of what I called it. And it has a very bizarre history. So in fact, this work of Spearman, he is called sort of a psychologist, but really it was one of the starting points for psychometrics. And actually the first place that discovered this algorithm that I'm about to give you was the psychometrics community. And part of the reason it got lost was because they described it as sort of an information theoretic thing about when the factors are uniquely determined given the tensor, but they didn't bother to state that not only is it unique, we found an algorithm to do it. So they proved it was unique by giving an algorithm, but they didn't have the language to say what makes this cool is we also have an algorithm. And that's partially why it got rediscovered in so many different communities, was because they didn't even call it an algorithm, even though it is. All right, so the various names I've heard of this, and this is not exhaustive. Sometimes it's called Chang's lemma, who was rediscovering it from Lurgens, Ross, and Abel, who in turn had forgotten about Harshman's paper. And the funny thing was, when I actually looked at Harshman's paper, Harshman doesn't credit it to himself. He says it was actually observed by Dr. Robert Jenrick, whoever that is. So I think the right name for this is, I think we've finally converged on the right name for this. It should be called Jenrick's algorithm. Now let me tell you how the algorithm is going to work, and then I'll tell you the conditions under which it'll work. So let's just start with what you should do. Given a tensor, your goal is to try and find the factorization, if you can, the decomposition. And what will be important is that the algorithm really does work under some conditions, and that under those conditions it finds the provably minimal rank decomposition, and that there is only one such rank decomposition. So let's do this one. So what's going to happen is we're given T is just sum from I equals 1 to R of UI tensor VI tensor WI. And let's keep things simple. So T is going to live in R n by n by n, but nothing about this will really depend on that. And of course, you're not given this factorization, but this is what you want to find. You want to find not just any rank R decomposition, you want to find the rank R decomposition, the unique one. Of course, there's some trivial conditions under which you can't do it, because the first factor is the same as, you don't know which one's 1 and which one's 2. So you can only learn these factors up to permuting their indices I. And you could also think about rescaling U at the expense of scaling V by 1 over that, or vice versa. So you'll never be able to recover them up to rescalings. But other than that, you'll be able to recover the actual factorization. So here's the idea. The idea is to reduce it to matrix questions. Now, the way we started off was the rotation problem that derived from Spearman's approach, that in general, given a matrix, you can't decompose it uniquely into what its factors are without imposing stringent additional conditions. But if instead you take this tensor and you flatten it twice to two different matrices, and the way we're going to flatten it is we're going to choose two different unit vectors, A and B, in Rn, and we're going to choose them at random, uniformly at random. You'll see where that comes up in the analysis. But now what we're going to do is we're going to use A and B to define two matrices that we'll get from flattening the tensor. So I'm going to let TA just be the tensor, which you get when you hit it with the vector A. So what do I mean by that? So, pictorially what's going on here is that you have this third order tensor, T, and now you have this vector A. So what you're going to do is you're going to take the first slice of this tensor and you're going to multiply it by A1, the first entry. You're going to take the second slice of the tensor, you're going to multiply it by A2 and add it up. You're going to take the third slice and multiply it by A3 and add it up. And so in that way, what A is doing is it's giving me a way to combine the matrix slices to get one matrix, and the coefficients that I use in the linear combination come from A. So all you're going to do is you're going to use two different ways of linearly combining the matrix slices, one given by A and one given by B. Now, just to make sure we're on the same page, here's a test your intuition. Let's say T is this rank 1 tensor, right? Outer product of U, V, and W. What happens when I take T of A? So what matrix do I get?
U times V times the dot product of W and A.
Perfect. W transpose A, and then UV transpose. The way to think about it is, in this tensor, each of the matrix slices is a scaled outer product of U and V. How much is it scaled by? It's scaled by the entry in W. And you just have that same rank 1 matrix scaled by different entries in W repeated throughout the slices. And then when I add up using A as the way to linearly combine them, all I'm going to do is I'm going to get some scalar multiple of what that rank 1 outer product was. And what that scalar multiple should be the inner product between W and A. Okay? All right, pop quiz number 2. Actually, let me do it this way. So what if I have a rank 2 tensor now? So what happens when I do the same thing? What matrix do I get? Too easy a question?
The sum of the above.
It's linear, right? It's way too easy a question. Just trying to make sure you guys are awake. All right. So, what this would be is it would just be W transpose A, U V transpose plus W prime transpose A, U prime V prime transpose. So this is the important thing, is that you have access to this object, this n by n by n array of entries. And what can you do to sort of tease out what its rank is? Well, what you can do is you can try adding up different cross sections through it. And what this is something that I can do given T. But I also want to keep in mind this dictionary of the things that I do to the tensor, how that changes what my representation is algebraically. This is something that I don't always have access to, what the decomposition is. But I want to think about the manipulations I do on the tensor, how they manifest themselves as manipulations on the algebraic representation. And the thing that we're going to exploit over and over again are just sort of these two facts, right? That what happens to a rank 1 object is easy to understand, and then you can extend it to arbitrary things just by linearity, by asking the natural question. That's all we're going to do. That's what Genric's algorithm will be. So let's try and use this now. So what are we doing? We have this unknown decomposition, and we hit it with A to create this. And I already said that from a matrix, you can't really recover its factors unless you put in really strong conditions, like orthogonality of the factors or something else, which imposes that the factorization comes from the SVD. But the trick that we're going to use is we're going to do it twice. That one of these matrices in isolation, we wouldn't know what its factorization should be, but when we have two of them, we know some relationship between them about what factorizations we're looking for, and that'll get us around the rotation problem. So to put it another way, I suppose I shouldn't spoil that yet. I guess let's keep in mind, so I'm going to do the proof simultaneously as I finish the algorithm, just so that it looks more intuitive. So, what is TA? Well, I claim what we can do is we can write it as U dA V transpose where dA is just a diagonal matrix whose entries are this. All this is think about the rank 1 case, right? We have one column, U, one row, V, and we get that the scalar multiple multiplying them is W transpose A, is the inner product between them. And this is the natural extension of sort of linearity that we already talked about, right? So does this make sense, everyone, that this is the form of what you end up getting when you hit it with A? This just taking the linearity and what happens to rank 1 things to the extreme. Now TB is similar. The only difference being that the diagonals are weighted by their inner product with B now, because that's how much a factor survives or doesn't survive. Right? So the point is that these two guys are actually related, which factorizations we're looking for. Or to put it another way, the next step in Genric's algorithm is going to be, what you do is you compute the eigendecomposition of TA times the pseudo-inverse of B. Now, if you, if you don't want to think about pseudo-inverses, just think about these as inverses, and hope that they exist. But this will work more generally even when the inverses don't exist. But the idea is, what does this product look like? So, using our scratch pad, if we have TA times TB plus, the pseudo-inverse, you can think about this as the inverse if you want to keep things simple. Well, what form does this take? So we can write it out as U dA V transpose times U dB V transpose, all taking the pseudo-inverse of this. And we flip these factors because we're, yep.
So I have a question. So the dA and dB, right? Do they have like either dimensions n by n?
Yep. It should actually, yeah. I mean, they only have R non-zeros though.
Oh.
Yeah. And the other thing to keep in mind is that this is highly order sensitive, because the entry in the first row, first column, if it's W1 transpose A, that means the first entry in U should be U1, its column. And the first row in V transpose should be V1, because that's the way in which I choose the right scalar to pair up with their outer product. So you have to be a little bit careful about that, but it's true. And what we're going to get out of this at the end of the day is you get U times dA times dB pseudo inverse times U plus. Now the important point is this is an eigendecomposition, right? Because the columns of U are themselves the eigenvectors. When I multiply by the first column in U, what I end up getting when I multiply by the pseudo inverse is I just get 1 in all zeros, which is going to pick out a diagonal entry, which then is going to scale the first column of U. So if you want to think about this with just inverses, imagine this was U times dA times dB inverse times U inverse. This would just, this would be a diagonal matrix, and this would literally be an eigendecomposition. So pop quiz number 3. So when is an eigendecomposition unique? Can anyone give me a condition? When given a matrix, its eigendecomposition is unique.
The eigenvalues are different?
If the eigenvalues are distinct, exactly. So this is where we're going to exploit the fact that we chose A and B randomly. Because if we think about it, one of the entries here is like the ratio of Wi transpose A divided by Wi transpose B. So there's basically no chance that they are exactly, that ratio is exactly equal for different i's. So that's the point, is that you're assuming that this will have distinct eigenvalues, and hence this decomposition is unique, and you can actually recover the columns of U. Now, doing the same thing the other way, what would you do when you compute the eigendecomposition of, so how would I compute the other factors? This is a way to compute the U's. So any ideas how to compute the other factors? Yes. Exactly. I do the same thing but flipped. So now I take the pseudo inverse the other way. When I take TB, TA pseudo inverse, what I end up getting is, make sure I do this right. Wait, I may have the wrong order. I have the wrong order. I have to double check this. Yeah, I messed that up. Let's do it the other way. So which way should I do it? TB pseudo inverse TA. That looks more correct to me. Good. So what are we going to get? We're going to get U dB U transpose pseudo inverse times U dA V transpose. And what we're going to get is V transpose pseudo inverse dB pseudo inverse dA V transpose. So now the same thing is true, that now it's just that the eigenvectors of the sky are actually the columns of the pseudo inverse of V transpose. So in any case, what you end up getting, what you end up getting is you get the columns of U and the columns of V from computing this eigen decomposition. And one of the remaining things is how do you actually pair them up? So any ideas for how you would pair up the columns of U and the columns of V that you figured out? So U, for example, is the eigenvector of this. U1 is the eigenvector of this with, is there an answer?
So the coefficients will be the same?
As in, I claim you can pair them up based on their eigenvalue. Because, for example, U1, when you multiply it, which eigenvalue are you going to get out? Is just W1 transpose A divided by W1 transpose B. And the same way when you have when you plug in V1 or the corresponding column of row of the pseudo-inverse, you're going to get actually the reciprocal of the eigenvalue. Just because one of these guys are taking dA and the other dA times dB plus, and the other you're taking dB plus times dA. So you have to be careful because here what you get out of the eigen decomposition is actually, V plus, not V, but then you take its pseudo-inverse to get V, and you pair up the columns of U and V, if and only if their eigenvalues are reciprocals. What?
They're the same because that's the pseudo.
Yeah. Not reciprocal.
Ah, not reciprocals.
But it's the pseudo. So the V.
So you would find V plus, and then you would compute V from it, and then yeah, you're right. I don't have reciprocals. I would plug them up if they're the same. But the final step is this would give me a way to compute the U's and V's up to, is there a question?
We do actually need a reciprocal because DAD plus is equal to DB plus DA, but then we take the pseudo inverse of V, so then we would get a reciprocal.
Yeah, as in the, it depends on whether I'm talking about the eigenvalue of this corresponding column of V plus or of V, but maybe let's not get too distracted yet.
These are not invertible matrices, but we're still computing some eigenvalues. Are they invertible?
So the thing that I haven't told you is, first I'm going to finish the last step in this algorithm, and then we're going to think about what are the right conditions where this thing works. So one of the conditions that I will need for it to work is not necessarily that this guy, that U be invertible, but that it have full column rank. So that would suffice here, because if it didn't have full column rank, then I couldn't really talk about recovering U. So let me state the last line of this, and then let me tell you the condition under which this will work. It's a little bit of a mouthful what the right condition is, but I think once you have the analysis in mind, it'll make sense. So the last step is actually to solve for the Wi's using T, which you know, equals sum equals I from 1 to R of UI tensor VI tensor WI. So you have the U's, you have the V's, and you've paired them up via reciprocal or not reciprocal, whatever, too early in the morning. And then you can compute the WI's from this linear system. Some of the things to check are that, first of all, why do those manipulations work, that we really can take the pseudo-inverse? That's a condition that we're going to need for this algorithm to work. And also, why should we should be able to solve for the WI's uniquely from this linear system? So let me tell you what are the right conditions for thinking about why Genric's algorithm works. And we'll finish up. So these are the right conditions to think about because, the issue is that, imagine you had, you create this matrix U, whose columns are the UIs. Now, one of the things that we crucially needed in the analysis was the pseudo-inverse here. Taking, for example, the pseudo-inverse of U. So there's no sense in which, when the columns are not linearly independent, the pseudo-inverse isn't necessarily unique. But the fact that the UIs are linearly independent is what's going to tell us that from the pseudo-inverse we actually recover the U's and so on. So the conditions under which Jenrick's algorithm works are a little bit of a mouthful to state, but these are the conditions which sort of get around the hardness results, is that if the UIs and the VIs reach linearly independent collections of vectors, and you can actually have a bit tamer conditions on W. Because what you really need from W is just that there's basically no chance that you end up having the same values repeated twice. So if you end up choosing in such a way that the WIs, no pair of them are exactly equal, then when you look at their inner products against a randomly chosen vector A, there's no way that they're going to be equal. So you actually need much tamer conditions on the WIs, but the theorem is, let me call this condition star because it's a mouthful. Even the statement of this, what it actually outputs, will be a little bit of mouthful too, but let me state it and then I'll explain it. The first thing is that you can never really hope to output exactly the same, hidden factorization because, which one is the first one and which one's the second one are completely arbitrary. So what you're going to hope is that there's a matching from the factors you found to the true factors so that you get the right things across it. Now there's another subtlety here, which is I can't necessarily assume I've recovered U1. For example, even after this matching step, because I could just as easily scale U1 and scale V1 down. Or I could create some other scaling that doesn't preserve what the rank 1 term is. So this last part will account for the rescalings that were allowed. So what you're really saying is after some matching of the factors you found to the true one, so this permutation pi from R to R, and then some rescalings that don't actually change anything, so you can change the normalization, provided you preserve the normalization of the overall rank 1 term, that after modding out by those equivalences, you really do find the factorization. So that's the statement for Generick's algorithm. So does the statement make sense? All right, and the last step, which I'm not going to prove, is that the last thing you need to show. So it's easy to show that based on what these eigendecompositions are, that what you get the UIs and you get the VIs up to scaling. You found them as if they were both unit vectors. And you pair them up correctly, too, because either their eigenvalues are the same or they're reciprocals. But the last thing that you need to prove is that actually this linear system is non-degenerate and really has only one solution, which would be the true WIs, but modulo the extra scaling factors that you've ignored so far. So that's the claim for Generick's algorithm. And just to give you a little bit of a hint about how we're going to apply this over and over again, is you can think about the sum from I equals 1 to R. This is some sort of hidden variable. So this is some latent factor that you don't observe is which of the R components is contributing to something. And then you can think about the entries in U, V, and W as being conditionally independent random variables. So what we're going to do over and over again is in our stochastic models, we're going to find 3 conditionally independent random variables, which are conditionally dependent on some factor we don't observe. Something like, for a document, what topic is it about? Or for a hidden Markov model, what is the hidden state? And as long as we can find 3 conditionally independent random variables, by virtue of Generick's algorithm, we're going to be able to use what we can observe to reverse engineer what the parameters of the models are via tensor decompositions. All right, so that's it for the day. So if you guys have questions, I'll take them afterwards.